Okay, so this is the very first slide. So radical is generally formed by homolytic bond fission. Homolytic means breaking when we have the same electronegative element. Suppose electronegative value is same like A and B, and I am saying electronegativity of A and B almost equal. So half over here and half over here. So it means it would form A radical plus B radical. So this is called radicals, and it is formed by in presence of heat or sunlight, and it is called homolytic bond fission. Homolytic, because there is no difference in electronegativity. And this is the free radical property. As you can see, suppose we have this one, the methyl free radical. And if you are going to figure out the electrons around carbon, you know that each bond can give you 2 electrons. So 3 bond around carbon, so overall 6 electron. So 6 electron means less than 8. So it is a electron deficient species. And electron deficient is also known as electrophile. And if you are going to find out the hybridization, you know that we have 3 sigma, so it would be sp2. And sp2 is generally planar in nature. Planar or trigonal planar, both are same thing. The stability of free radical is same as carbocation. I can say yes, same as carbocation. It means tertiary, then secondary, and then primary. Yes, always sp2. Yes. Means, yes, it's sp2, especially in DAT. So, 6 common steps in radical mechanism. These are the 6 most common steps. The very first one is a homolytic cleavage of X2. This is X2 basically. So half here, so you have both the radical. Second one is addition to a pi bond, means we are going to add X over pi bond. And you know that carbon double bond carbon, we can break like this. We can break like this. Half here. So one is CH2 radical, another one is CH2 radical, and here we have X radical. So this X and CH2 is going to combine because they both have radical. So you can see CH2 with X and this CH2 have a radical. Make sense? The third step is called hydrogen abstraction. It means halogen is going to abstract the hydrogen from hydrocarbon. So this hydrogen, we have a radical over here and X have a radical. So X would grab this H and R have radical here. So this is called hydrogen abstraction. And the next is halogen abstraction. So halogen abstraction means R is going to abstract this X. So it would be Rx and plus X radical still. And the next step is elimination step. So this X is going to eliminate. So you know that it would donate the electron to this carbon and this radical. So it would form a double bond here. And the last step is the coupling one, where both the X radical is going to form a single bond. Yes, generally in DAT, this is basically Orgo 1 and Orgo 2 as well here in this mechanism. But in DAT, you have to memorize only the 3 steps for free radical mechanism. The first one is called initiation step. Initiation step. The second one is called propagation step. And the last one is called chain termination. termination step. Clear? And I will tell you the trick how you can memorize what is initiation, propagation, and termination. So don't worry about the top one. This is just information. Those steps is common in radical mechanism. So don't worry about it. Let's start the first free radical halogenation using bromine. Free radical halogenation. So this is also called bromination. Bromination, and it is selective one. Selective means it would give you the most stable radical, and then bromine is going to add over the most stable radical. For example, we have this compound. So first you have to form all the possible radicals. So the very first one, we can draw this one as a radical. The second, we can draw here. The third, we can draw here. The fourth, we have here. And the last, we have here. Make sense? These 5 possible radical positions here in this case. It makes sense? Please tell me. Now let me know which one is the most stable out of 1, 2, 3, 4, and 5th. Which one is the most stable? Of course, number 2, because it is tertiary one. So the Br is going to add over the most stable one. So we have bromine at this position. So there is no rearrangement, because rearrangement is a property of carbocation. And here free radical is an intermediate. Now this is the mechanism. Now this is very, very important. So in initiation step, this is my Br2, and we can represent Br in this way. So it would break like this homolytically. So you have 2 Br radical. So in initiation step, product have radical, only product. Next, propagation step. Propagation step means, look at the wording. This is called hydrogen abstraction, and this is called halogen abstraction. Okay. So first Br is going to grab a hydrogen from hydrocarbon. So we have a most stable radical, and then this radical is going to grab a halogen. So this one is called halogen abstraction, and the top one is called hydrogen abstraction. So now you can see in this is the chain propagation step. So you have this one as a product. Here the Br is going to attack on the most stable radical. And the last one is called termination, where both the bromine is going to couple. So last step is known as coupling. So initiation, where the product is radical. Propagation, where both side is radical. You can see the first step product and second step reactant. And the last one only reactant have radical. Make sense? So hydrogen and halogen abstraction is a part of propagation step. Clear? It makes sense? Perfect. So now we have the problems here. So predict the major product in bromination one. So you know that we don't have a hydrogen here. We have a hydrogen over here. So it can be a radical. So the most stable radical would be this. So Br is going to add here. So final product would be this. Here, in this case, we have a possible hydrogen. So it would be the most stable radical. So Br would be here. And the last case here, the bromine. Make sense? Please tell me. Always figure out the most stable radical. Free radical halogenation using chlorine. This is very, very important. So chlorine is not selective. It means it would give you the mixture of all the possible products. So if you look at this reactant molecule, the possible radicals are this one. The first, second, third, fourth. So these are the possible radical, and we have a mixture of product. Make sense? Please tell me. No major, no minor in this case. Clear? And again, the same mechanism. The first is initiation, where both the halogen is going to break and that would form a radical. The second step, hydrogen abstraction. Chlorine is going to grab this hydrogen and we have a radical. And in the next step, halogen abstraction. So radical is going to grab this chlorine. So in the last, coupling. Makes sense? So here we have multiple products. So in propagation step, it can grab this hydrogen as well. This hydrogen. Okay. The chlorine can grab this hydrogen. So there is another possibility. Clear? So this one is just a one example of this particular radical, but it can give you multiple products. Make sense? You can see same pattern in propagation step. So here we have some, we have to ignore the stereoisomer. What does it mean? It means if any of the product have chiral center, then you know that it has two stereoisomeric product, like one is R and one is S form. So here in this case, the possible radicals are this one. So these are the most, the possibilities we have. So overall, we have 5 product. Make sense? Oh, we have, I think, another one, this one. We have another one, this one. Clear? Yes, 3 is the most stable, but it would not give you the major or minor product. It would give you the mixture of all the possible product. Make sense? So we can't say the third would be the major one. No, it would give you the mixture of all the possible radicals. So we have 6 radicals here. So here when butane undergoes a radical chlorination, 2 constitutional isomer are obtained. The product have 2 chloro and 1 chloroformer has a new chiral center. In this case, a racemic mixture of 2 chlorobutane is obtained because the structure of radical intermediate is trigonal planar. So look at this example. So especially at this position, at this radical, you can see when you are going to add a chlorine here, so you have a chiral center at this position. So whenever we have a chiral center, you know that it can be either wedge chlorine or it can be a dash one. So we have 2 isomeric product. Make sense? Clear? Halogenation at an existing chiral center, it means we have a bromination, so most stable. This is the most stable, you can see. Okay, first of all, this is not a chiral center here. You can see this is not a chiral center. This is also methyl, and this one is a methyl. It should be a hydrogen, then we can say. Make sense? If we have a hydrogen here, supposed to be like this. This is the radical, and now you have a bromination. So this is Br. Now this is a chiral center, so you can represent one with the wedge and one with the dash like this. Clear? This is not a chiral center first of all, because this is dimethyl, and you know that any carbon can be chiral when we have 4 different things. Make sense? Don't worry about wedge and dash. Wedge and dash is just a mode of representation. So next is formation of diastereomer. You know that this is the most stable radical because this carbon, we don't have a hydrogen here. So you can say one on the wedge, one on the dash, and this chiral center you can see remains same. That's why we can say diastereomer. Make sense? You know that when one chiral center has no change and one chiral center have a change, then that is called diastereomer. It does not affect the, yes, it would not affect the alkene because it can affect alkene when we have only Br2 or HBr. Make sense? Whenever Br2 with the HNu, that is always free radical reaction, and free radical is a part of alkane, not alkene. Make sense? So that's the difference between Br2 with H nu and HBr. Next is allylic bromination or allylic benzylation. What is allylic? Allylic means suppose you have a double bond and this is called sp2 carbon. So neighboring sp3 is called as allylic carbon. And what is benzylic? Benzene outer carbon is called benzylic carbon. This is called benzylic carbon. So benzylic or allylic bromination means you have to add bromine at allylic or benzylic position. So this is my allylic. So you have a bromine here and this is my allylic. So we have a bromine. Clear? So you have to do allylic bromination. So this allylic position is in the resonance, you can see. So now you can draw its resonating structure. So we have two possible radical, you can see. Make sense? Please tell me. Is the left one is, listen me here. It depend on KCP and TCP. KCP is called as when the intermediate is more stable. So if you compare A and B, these are my intermediates. Which intermediate is more stable? Let me know. A, yes, because it is tertiary with resonance, tertiary plus resonance. So this product is called KCP product because intermediate is more stable. But in this case, my intermediate is less stable, but product is more stable because this double bond is more substituted double bond. So when highly substituted double bond, that means more stable product. So this is called TCP. So TCP means thermodynamically controlled product in which product is more stable, and KCP means kinetically controlled product where intermediate is more stable. Make sense? So it depends on the language of the question. Yeah, it is more useful once you have a conjugated alkene, okay? Then you can think about KCP, TCP. But here I can say here KCP when intermediate is more stable, reaction intermediate is more stable. And TCP thermodynamically when product is more stable. Allylic carbon. An allylic carbon is a carbon atom directly bonded to carbon-carbon double bond. We have done this. This is my allylic. This is my allylic. Now this is the mechanism. Here we are using NBS. NBS is called N bromo succinamide. This is succinic acid. So once you have a amide group, that is called succinamide, and here we have a homolytic bond fission. So we have radical and this radical. This is called initiation one, and in the next hydrogen abstraction, so Br is going to grab this allylic hydrogen. So you have this position, and this is in resonance stabilized. Okay, no need to draw the resonating structure because it is identical. So if you are going to draw, you have this one and both are same one. So no need to draw its resonance structure. And then halogen abstraction. So radical is going to grab this bromine. So you have allylic bromination, and the last step would be the coupling one. Okay. So this is the final product. Next is auto-oxidation. This is very interesting. In the presence of atmospheric oxygen, this is atmospheric oxygen, organic compound are known to undergo a slow oxidation process called auto-oxidation. This carbon have a hydrogen. This is methyl. This is methyl. So nothing you have to do. You have to add this O2 with carbon hydrogen bond. So simply you can say OOH like this. Clear? So this is called peroxy bond, peroxy linkage. Make sense? This is the mechanism of anti-Markovnikovs with the HX because it is also free radical type mechanism. And you know that first step initiation where this peroxy bond is going to break. This is my peroxy. So half here, half here. So you have radical, and then this is going to, this HBr is also going to break. So you have a Br radical. Next is propagation. So addition of this bromine over this alkene. So this is addition step. All the 6 step here, okay? And then we have hydrogen abstraction. So you have this product, and the last step is a termination one, which is a coupling one. So you have this. Make sense? Please tell me. So in this chapter, 3 things is very, very important. The first, Br2 with H nu, which is selective one. Selective means most stable radical would be the major. The second thing, Cl2 with H nu, that is non-selective. Non-selective means mixture of products. Mixture of products. And the last one is NBS. NBS gives you allylic and benzylic bromination. Allylic and benzylic bromination. Make sense? Please tell me. Perfect. So this is all about the free radical one. So my plan is to discuss each and every chapter in a single sitting. So this time we are done with free radical. In the next class we will do Diels-Alder and then Grignard. Okay. Any doubts? Thank you so much, guys. Bye bye.